Yeah. Okay, so quadratics. The first thing in quadratics you need to know is how to complete the square. And before we go into how to complete the square, you need to understand why do we want to complete the square. So think about this. If I have a quadratic, let's say x squared plus 2x plus 1, and I want it, and I have a function. This function is this quadratic. It's what x squared plus 2x plus 1. And I want to find the inverse of this function. If I try to make like x as a subject and like take this to the other side, take this and then divide by 2, and then you're gonna have x on both sides, and then you're just gonna be stuck in a loop. It's just gonna be like y minus x squared minus 1 over 2 equal x, and then you take this and you put it into x, and it's just a loop and it's not gonna work. If I wanna actually find the inverse of this function, I need to think of it in another way. And this way is, how do I put x on one side and everything else on the other side? So actually, every quadratic in the form like ax squared plus bx plus c, every quadratic could be written in such a way that, every quadratic could be written in this form: a into x plus p squared plus q. Now, why is this useful? Let's say we're finding the inverse. Let's say this is equal to y. You can easily just make x the subject. Um, Now, why is it that every single quadratic could be written this way? Uh, let's think about it. A just controls the first number. So like this a is the same as this a, because after you expand this is just going to be x squared, so a x squared. So this controls the first number. Okay, and then p controls the second number. So when you expand this, it's just going to be 2px, and then you multiply it by a. This way, ap is just going to be equal to b. So you can change p to control b. And after this, you're just going to have p squared plus q. Okay, this is going to be equal to c. You could set a value for a such that it's equal to the ax squared, and then change p so that's equal to b in the bx squared, and then you can change q to control c. So you can write every quadratic in this form. The way we usually do it is, uh, you take this, you divide this by half, and then you remove this number squared and then plus 1, and just that's how you usually do it. But why do we do it this way? Why is this like, why does this work, you know? If you can check the answer, it works every time, but why? Okay. We can represent each of these variables, and like you can represent this and this as areas. So if this is x, this is x, so the area of this square is x squared. And then if this is 2 and this is x, so the area of this square is again 2x. And then you just have a number 1. I want to write it in such ways it's something squared plus a number. So let's try to do this. If I take this, this has a side of x, so this side is equal to this side. If I divide this by 2, okay, this is gonna be 1, this is gonna be 1. You're gonna have two rectangles, which is gonna be 1x and then 1x. If I take these and stick them right here, what is gonna happen? Now let's see. If I take this and put it here, you're gonna have x, and this is gonna be x and 1x and 1. It's almost a square. It's almost a square where each side is x plus 1, but you have this missing part. Now this part, uh, is gonna be 1 times 1, which is 1 squared, which is 1. So what we can say is the total area is the area of the squared, of the square, minus this area, so minus 1 squared. And then you're just gonna add back the constant, and then these two cancel out and you get x plus 1 squared. So that's why it works. Now things get a little bit more complicated once you go into numbers, into quadratics, where the first number is greater than 1, where a is greater than 1. So instead of x squared plus 1, let's try another one. Let's try f of x equal to, let's see, 3x squared plus 6x plus 9. Yeah, let's see if this is our function and we want to write this in a completed square form. Let's try to do the same thing again. It's 3 of these squares, so x and x, plus 6 into x plus just 9. If we try to do the same thing, we take this x and x, and then you divide this by 2, and it's 3, 3. You take 3x, and then 3 and x, and then you move this part, so minus 9. So you get x plus 3 squared minus 9. But there is still 2 of these squares. There is still 2 x squared squares, you know. So what we do is, instead of taking the full rectangle here, we divide it into 3 smaller rectangles. So this is 2 and x, and then you have 3 of these times 3 plus 3 into x and x. So you have 3 of the bigger squares and 3 of the smaller squares. So let's take just into consideration, let's take into consideration just one of them. Yeah, we do the same thing again, and it's just x, x, and then you divide this by 2. So you're gonna take 1 and x, and 1 and x, and then this is 1 squared. So you take x plus 1 squared minus 1. You could actually factor out the 3 here as just 3 into this. Yeah, so this is for 1 out of the 3. This, what we did here is this. So we need to multiply it by 3, and then finally don't forget to add the 9. Yeah. So plus 9. So what you're gonna end up with is x plus 1 squared plus 6, and then this 3. Sorry. Yeah. Now let's try to do this for a more general solution, you know. Instead of doing this every time, let's think like the most general quadratic. It's ax squared plus bx plus c. Yeah. Let's try to apply the same thing. So you take the a out. It's x squared plus b over a x plus c. You can check actually that last time we actually took the a out. Like it was 6. We made it 2. So that's why we factored out the a. And then you now some people just prefer to use this. It's a big formula. It's an annoying formula, but some people prefer to use it. I don't. But this works every time. If you use our example from earlier, it's just three. It's the same thing, but it's not intuitive. It's a big format. It's actually annoying. But what this helps us with is we can actually solve quadratics this way. Remember you had like this, like how would you typically solve this without the quadratic formula? You can say factorization, but factorization doesn't work for every single case. It's not a general way to do it. So how would you solve this? Well, actually, uh, you could solve it using the completed square form, and then you can just take to the other side. So I'm just gonna spare you the details here. It's too long. And then you can see actually this is the quadratic formula. If you do like just two more steps in simplifying, just multiply this by 4a, because this 4a squared, and then after you take the square root, it's going to be minus b plus or minus square root of b squared minus 4ac, and this becomes 2a. So, and this is also 2a, so 2a. Yeah, so that's where the quadratic formula came from. Another good thing to know about the completed square form is that if you have a quadratic that it's ax plus p squared plus q, it's in this general form. The turning point is actually minus p and q. Why is that? This is gonna be a bit more clear in the transformation chapter, but if I have a function, let's say I originally had x squared. What did I do to get from x squared to this? Uh, Instead of x, it became x plus p squared, and then you multiplied it by a, and then you added q. So that's what happened. So instead of the input being x, instead of putting x, you actually like if you have f of x uh, equal to x squared, instead of me putting x, I put x plus p. So instead of the input being x, the input became x plus p. So if we have our graph, this is y, this is x, and this is y equal x squared. So instead of at x equals 0, instead of giving you the actual input, sorry, let's say x equal to minus p, instead of giving you the actual input of x equal minus p, I gave you x is equal to minus p plus p, so which is 0. So instead of this being your input, like this x being your input and this being your output, no, you took the input that's right there. So yeah, you kind of pulled the graph like this. So when you're doing, like, you're not taking your x, you're just taking someone else's x, and you pull the graph to the left. That's what happens when in the first transformation. So this becomes your graph, becomes like this, and then the turning point has an x at minus p, and then you multiply it by a. That just stretches the graph upwards. So instead of becoming like this, it becomes like this. That's of course assuming a is a positive number greater than 1, and assuming that p is also a positive number. Also q. Yeah. And then, so that's your new graph. And then you added q to the whole thing. So instead of this being your y, you just added q to it. So it became minus p and q. So that's what happens to the turning point. This is minus p and q. Yeah, so that's what happens to the turning point. Now, why specifically minus p and q? It's because it started at 0 0. If it started at any other coordinates, it's gonna be different. Okay, it's just gonna be the x coordinate minus p and the y coordinate plus q. Yep,
So that's it. Yep.
that's it. Uh, I hope you enjoyed the video. I hope this was easy. I know it's a bit of a long explanation, but this is gonna be very helpful in the transformation chapter. This is gonna be very helpful in many other ways. And now you know where the quadratic formula came from. Okay, thank you.